Não, pode gravar os dois. Quando terminar, você pode terminar.
Hello everybody, and welcome back. Yesterday we started looking into but we didn't quite finish. So I would like to take a little time of today that we finalize the turbine version and then move on to Alchemy derivatives. So yesterday we went up until here where we calculated the Coulomb matrix and I brought you, so this is the day before I put some example codes online on the course webpage, so you have everything and can use that for the time being. So in principle there are two solutions. The indentation seems to be off. 1 second. So we had two functions. So we discussed two ways to do that. This is the one that we did together, right? So for the Coulomb matrix, there was the nested iteration. So the idea is for the Coulomb matrix, we have to implement this. That the ith and jth element of the corresponding matrix. On the diagonal is the nuclear charge transformed 1/2 nuclear charge to 2.4. And on the off diagonal element, the product of the charges divided by the distance. And the way we had solved that was that first we figure out how many atoms there are. Then we make a new matrix, a square matrix with all zeros. And then we iterate over all rows and all columns. Then depending on whether, see, it's not correct. If the two if we're on the diagonals, so the I and J are identical, then we put the diagonal element there, and otherwise we calculate first the distance and then have our matrix element. And at the end, we didn't do that yesterday, but in the end, task said that we were supposed to make this a vector. So far M is a matrix. We want to make this a vector because it's later on easier with bookkeeping, especially if you want to have the representation such that you can move into scikit-learn, which wants you to get the vector rather than the matrix situation. Is that code clear? Just refresh this. Yeah, now the indentation is actually right. So is that code clear? Is there any questions on what it does? All right, then let me illustrate, and if you can illustrate a little bit how you would do this with NumPy alone. I just want to sketch the idea on how it works. Because the calculation that we have here, numerically, is very inefficient. You have these two nested for loops in Python, and control flow in Python is slow. So compared to compiled languages like C or Fortran, you easily lose 3 orders of magnitude in performance. So you want to avoid that in practice. For what we're doing here doesn't really matter, but once you do actual numerics, that will matter. And of course, there are a few obvious tricks that you can exploit. For example, the same way as we did this the day before yesterday, you can exploit the fact that it's symmetric, right? So you don't need to recalculate the upper and lower triangle, but that's not what I meant. I want to discuss this thing with you. And I'm going to draw how it works. So positions was the vector of n, x, y, z, right? So you have n atoms, you have the corresponding positions, the 3D spatial positions. The x, y, z components as the 3 columns of our 3 by n matrix. Those positions. So now what we need for the distances is all pairwise distances. And we know how to calculate the distance. Right? There's the norm evaluation. So this is a pure NumPy solution to the problem. Again, the norm. But you have to calculate all the pairwise interactions. And we did that again the day before yesterday, using the non-slice or the new axis. So effectively, that first thing that you have here takes the full array of positions, but in the end adds one more axis. And that turns the argument of the norm into an array that has, sorry, n of 18. This case is 18, but in general it's n. N by 3 entries, the 3 tensor. Because positions is n by 3, and now you take all pairwise combinations though. And with the optional argument axis, you specify over which axis you calculate the norm. That would be 0, 1, 2. So it means you always take the 3 x, y, z entries to calculate the norm. If you don't feel comfortable with this here, that's in the Python course. If you scroll down, there's something on NumPy. This is discussed with the advanced indexing. If you want to read up on it, especially that trick, because it's so common in chemistry, is discussed there with some examples on what this does on arrays. There is also the function in SciPy, spatial pdist. So SciPy is a companion module to NumPy. NumPy does well in numerical Python, and SciPy does scientific Python. The difference being that NumPy focuses on the low-level math, and SciPy focuses on higher-level algorithms. This is not exactly sharp, the separation, but usually people will use both together. And pdists can very efficiently, even in a parallelized manner over several cores, calculate pairwise distances of vectors. So if you don't feel comfortable with the array projection and indexing, then pdist basically does the same thing. Okay, so that is a very efficient way of writing this, where the loop happens in NumPy. It doesn't happen in Python, and therefore it's cheaper. What you do is you calculate first all pairwise distances. That's our n by n matrix. Now the next thing it does is to set all the diagonals to 1. Why is that? Because what we need to calculate is 1 over distance. The distance of a point to itself is 0, so 1 over 0 gives 1. So the next step sets a diagonal to 1. Now, what we need to calculate is the product of the nuclear charges, right? So the ith and jth entry of the off diagonals have the ith and jth nuclear charge as a product. And how do you call this? If you have one vector and another vector, what you calculate is the product of all possible combinations. It's called the outer product. The vector product is the scalar product, and when you transpose one into the pairwise combination of the two, that's the outer product. That's exactly what you can use in NumPy. Again, does all the combinations directly. NumPy.outer takes the outer product of the vector of the nuclear charges with the vector of the nuclear charges. So that's basically Zi times Zj for all of the ones. That means that this is the matrix that will return at the end. Is Zi times Zj divided by distance, so all off diagonals are correct. And then you can update the diagonal of the matrix to have a certain value. So this fill diagonal is used twice, once with the same scalar value. With a scalar value, then every entry along the diagonal is set to that value. And if you give a vector, then the diagonal vector is replaced by the new values from that. So you don't need any for loops in Python itself. You can keep everything in NumPy. That will take some time to get used to. So for the purpose of this course, it's probably a good idea to write this very instructive nested for loop so you understand exactly what's going on. If you want to use this later on in your work, and you'll find yourself using it, it's probably well invested time to understand a little better what NumPy indexing and slicing does. Any questions so far? So the high-level picture is the important part for the NumPy that you have an idea of how to report it. Okay, now I want to do the last task from yesterday. Otherwise, it's a little bit like leaving you hanging. So you remember in current bit regression, we need some kind of training data, and we need a representation, right? So the representation we just calculated, that's our Coulomb matrix as a vector. And you have those functions where you train a model, right? Where you get the model coefficients, you wrote it yesterday. Where this is the kernel matrix, and the kernel matrix element was the kernel function. That was the Gaussian kernel from yesterday. And those xi, so far, they were just values. Because we did this 1D example. Now you're going to use the Coulomb matrix. So you have the geometry. There was this one, right? Which gives us the naphthalene, that particular matrix. And now we would like to use that one together with the nuclear charges for actual molecules. I will show you what this looks like first. We have an idea on which variables we need. So let me generously copy this code over. Feel free to take the code from the page. So we need this. So you get geometry. We need NumPy for that. And that was the matrix of the coordinates, right? So of our naphthalene, that's the x, y, and z coordinate of all the 18 atoms. And now we also need to take the function get data, so I can explain to you what you see there. So get data you run this, returns two things. The first one is an array of nuclear charges. So we can do something like charges, energies, and then I can show this. Charges.shape should be 2,286 data points. That's how many molecules we have in that database. And it has 10 values. Why is that? Every of those, each of those molecules in the database is given by its nuclear charges only. We have naphthalene. Sorry for my very physicist-like drawing of molecules. So now there's a fixed order of the atoms. The exact order for you doesn't really matter. But what you have in charges are the 10 nuclear charges on those sides, which are carbon and naphthalene. The hydrogens don't change. For all 2,000 molecules, you have the same number of 8 hydrogens coming up there. So your coordinates that you have, your coordinates is 10 carbons and then 8 hydrogens. So if you wanted to get the real nuclear charges for the molecules in the database, that's one row of this charge array, and then 8 times 1 after that. That's the nuclear charge. Is that clear? Which means that let's have a look at what's in my first row. Your first row will be different because they're shuffled. They're sorted randomly for reasons that I can explain later. So in my first row is 6, 5, 6, 6, 7, 7, and so on, which means carbon, carbon, nitrogen, right? And that's one doping pattern. So this means we take our naphthalene, we have the same geometry. Now we change the second atom, for example, this one, to a boron, and then it stays the same. This becomes nitrogen, and so on. So that's the doping pattern that you have in this charge vector. Since the hydrogens are never doped, they stay around. This is the beginning, and then you add 8 ones after that. That is the set of nuclear charges, and the coordinates they are always the same for all molecules in the database. The positions of the atoms don't change. Is that clear what you have? Then energies, the second thing that get data returns, is the 1D array of 2,286 entries. So for every of these molecules, for each of those doping patterns, you have a new energy. And those energies are calculated with quantum chemistry codes, so reasonably expensive. But that's our data set. So what we want to learn is exactly this. That energy is what we want to learn. Any questions up until here?
No, it's just people trying to get into the room.
All right. So what do we need to do? So the task says to take 100 molecules. So you can take the first 100 of those, That's why they are shuffled, such that you have a randomized data set, because otherwise they're generated repeatedly. So you take a bunch of molecules, that's your bag of molecules. For each of those, we need to calculate the Coulomb matrix representation. So we get one vector for the first molecule, one vector for the second, and then one for the last. So in total, that's 100 of these vectors. Now each of those vectors gets assigned the corresponding entry and energies. This is our representation, and we have the labels. That would be what we have is xi on the previous tasks. Then we have the y vector, which contains 100 energies. It's basically 100 by 1 vector. Those are the corresponding energies for the first 100 molecules in your bag of molecules. Now you take those vectors and you calculate the kernel matrix, which is 100 by 100 matrix, where this one, the I and the j entry, is the Gaussian kernel applied to the I and the j vector of our representation. And afterwards, we do the same as before. And what we did yesterday. That gives us the alpha prediction. Then in the query, again, you do the same as yesterday. You take those alpha vectors and you compare the next 100 from the back and get a prediction for the end. Does that make sense so far? It's the high-level direction here. All right. Then let's try to do that. Feel free to take the code from the web page if you don't trust your own, or if you lost it or whatever. If you get stuck, let me know. If you want to see the code, you have to refresh the web. Yes.
Should we use the code from before to train the code? Or
You can. So you can reuse the code from yesterday, right? If you solved it yesterday, just use the code. The logic is exactly the same, right? So the task is designed such that you can now just switch to more. So if you implement it correctly, then this will work.
so this is one more question. So for
Just
the
one.
the first question is like, so we want to do the x and y's. The x and y's are the charges and then because so the x is just the Coulomb matrix. So we are correlated with the matrix to that.
Yes.
Using the universal. Isso aqui então, todas as coisas. Só que essa foi a versão que eu escrevi no livro de Falk. Essa foi a versão que essa é a versão mesmo seguinte. Uma função substitui a outra. Então, nós vamos usar essa mas eu vou deixar aqui. Porque eu fiz os cotonões. Outros, em tese, era isso uma, eu acho, mas não é mais eficiente. Se eu copiar, esse tem que copiar, né? O que eu quero? Eu tinha você quer relações internacionais e aí você vai colocar essas relações faz diferença você vai colocar um fator multiplicadas o fator que você já multiplicadas é o resultado desse vetor que esse é o vetor em cada x aqui vai multiplicar para estimar o valor de uma função.
So you need this to get the Gaussian kernel. The indentation is gone. We'll fix it in a second. So that contains the code for the Gaussian kernel prediction, which is lowercase k. And the next box contains how to get the alphas. And that one is the prediction.
Que a gente não calculou essa função para poder ser nós de x e y. Então, essa função de verdade é definida os cruzamentos para estimar então, você vai tirar cada x desses aqui com uma relação. Só que a questão é a seguinte: se essa função está muito longa, você dá um pouco dessa função. Só vai ter dois pontos mais próximos. Faz assim, esse aqui primeiro, eu fico bom esse criar, que vai fazer a diferença dos dois pontos e vai calcular na hora do depois. Depois disso, você tem o nosso kernel, ele vai simplificar esse kernel dos pontos. Então, o que é basicamente coisa que eu fiz? Você pega o valor, você compra uma matriz do grupo, você tem também o seu e aí você que faz para todos os marcos que estiver na diagonal, dois pontos, dois pontos, eu acho, dois pontos e eles são dois pontos. E fora isso, você tem primeiro depois coluna. Aqui o I é as linhas, essa matriz e o J são as colunas. Então aqui faz o que é para todos os possíveis pontos, todas as diferenças você tem esse ponto. Você tem esse ponto 2 e aí você vai ver os pontos em volta. Se o ponto está muito longe, ele não contribui para o valor da função. Então isso aqui esse ponto faz, ele vai estimar o valor tipo assim, x igual a 2 é mais difícil. X mais 5, por exemplo. Esses pontos na solução, os pontos de treino. Como que a gente gera isso aqui? Supervalores de x entre 0 e 6 aleatórios. E aí você calcula o potencial de nosso price e aí você estima o valor da função assim, e essa é a rate do teste do valor disso. Eu tenho aqui uma linha horizontal que vai de 0 a 6. O valor aqui que eu tenho essa predição, certo? Eu não consigo ver se inclui o valor da função aqui. Diferença prática é como que você constrói a apresentação das documentos, que é o que na matrícula essas três pessoas. Você tem que dar essas posições, as cargas, e vai chamar o array que é a matrícula. Esse array é a matrícula é a representação do machine learning da sua molécula. Aqui a gente tem as coordenadas, porque ele deu essas funções de geometry, o get geometry utilizado por os SM, que são os irmãos, e aqui as cargas e energias dão as cargas e a energia. A energia é o nosso uso. E a matricula que a gente usa as cargas de exposição é o X. E é a nossa representação da molécula. Que é o exemplo e a descrição. Essas cargas, colocar essas cargas todas aqui, porque cada vez que você faz uma verificação diferente, você pode fazer assim, você tem essa teste, eu posso ser mais porque isso já vai ser outra vez. E isso também só por Nesse caso, agora do Guido das moléculas, agora eu vou fazer o front do esse vídeo está certo. Se tiver certo, eu acho que o que eu tenho que fazer é a função para ver o domínio. Ver onde a função está mudando, se acaba isso aí. E aí, funções isso já foi então, esse vídeo é as alfas. Qual que era o não, canal? Os alfas são os coeficientes que multiplicam cada você. Então, a questão é a seguinte: esses alfas são mais difíceis. São mais caros, né? Funcionamento, porque esse vídeo da ideia tem uma inversão de fatura aqui. O custo dessa inversão de fatura é maior do que se isso não demorar muito, você pode salvar esse cálculo aqui. E aí você pode carregar ele para fazer materiais diferentes. Porque só não está nessa função de edit. Você só multiplica o seu item, você pode mudar o seu item, então, que você quer prever, e usar os mesmos palmas. Eu acho que vai explicar isso. Eu quero ver se funciona. Tem que trabalhar um vetor de 100 entradas. E pior que deu uma função de não na curva, na eu ouvi dele. Eu li que eu uso essa curva
That's exactly what it does.
de 100. Tem e a outra então, se eu fazer essa operação, essa parte de função de uma variável, meu problema. Então, o problema é essa distância. Tá. Agora, a mesma vez que 100% por 18, você tem 18 átomos por 18 átomos. Somente. Tem que jogar assim. Ou esse eixo de diferença. Você tem que Another question was, I had a mirror in the cool matrix which says that sorry, I just bringing some coordinates here, but it says that the operands could not be broadcast together. So in the yeah, but I just close your clothes. But I just go with your code, so they were using this line here, so I'm not sure if I did something wrong. When I use the codes, you just copy the reference. This counts as the coordinates. That's the name. We just got the coordinates function. And then I got some arrays of 100 charges. And then I try to make it with the geometry. As coordenadas x, so x e só olha aqui, aqui, as coordenadas y, porque ele falou que eu estava colocando uma defesa. Eu tenho que colocar só uma dessas. Cada uma dessas é as cargas de uma molécula. A Charles, se você ver aqui a Charles cheio, a gente só vai chamar uma informação. Esse cara diz o seguinte, 2.236 cada uma dessas entradas usei 10 marcos. Seja, por exemplo, zero, você colocar uma média. Acho que isso resolve. Mas o que interessa aí ele está citando que estando perto mais distante os três ao que investe ao valor ou você faz isso para fazer o que você precisa ter isso você pode imaginar você já são modelos depois eu tenho esse médico o governo ele é justamente o vetor que são da processo a gente cada vez um ponto e outro ponto. Para você estimar o valor econômico, você precisa saber por quanto você vai multiplicar o seu e aí, esses preços, esses alfas, você multiplica os alfas, aí você pode fazer a predição. E aí você pega a empresa que você não viu, você fica prevendo essa propriedade do caso energético.
Very fun.
Não, eu sei.
That's what you see there.
Não, eu produto o que aconteceu? É perfeito, mas a gente tem que colocar um vetor de esses 10 aqui são só as cargas dos carbonos. Então a gente tira a posição do hidrogênio, ou a gente adiciona carga. É o seguinte, as cargas ele não vai considerar, mas as coordenadas eu tenho que tirar ou tira esse hidrogênio, ou põe o hidrogênio. Aí eles compram isso. Na verdade, a gente quer estender cada eixo, por isso esse eixo aqui foi 10 para 18, e esse outro eixo aqui tem 10 para 18. Isso é só coloca.
Em vez de multiplicar, colocar.
That's for the training day. And they use that first out for
Eu estou dentro porque ela funcionou. Eu aí coloquei os dois lados. Mas eu acho que eu vou tirar os. Porque é o seguinte, quando você as coordenadas que as cargas que colocam são só as as posições são. Primeiro eu pego aqui a geometria, que são as coordenadas. Aí eu pego essas todos já estão distantes, aí eu pego só 100, como ele não já for.
Oh my gosh.
essa função vai tornar as coisas que são várias. Tem que ter procedimentos. Mas quando eu não aqui na shape,
on those training. That's why. So, training techniques. That's basically that thing.
as áreas
So here, alpha is amazing. Here, it's just
uma coisa que precisa ser teria que ter aqui viajando, isso aqui é um dos outros por três.
some all of the together.
Isso que eu não sei jogar, isso que eu acho. Ou seja, você tem dois primeiros que são você pode olhar tradicionais setores em dois eixos.
This is one training.
Depois de uma matriz. What you see here is what nessa função aqui, x é elevado, e a carga de uma molécula. Isso coloca we are discussing whether we need to do that. So,
Let's start together. We look at that step by step. What needs to be done? So I have the code that, given a geometry, calculates Coulomb matrix. So I will just copy the code from here for the Coulomb matrix. All right, now the Coulomb matrix of the positions. Positions is what you get from get geometry. In my case, that's the variable geo. Now the nuclear charges. Yesterday, we looked at the naphthalene itself. So that is 10 carbons followed by 8 hydrogens. So what we did was 6 times 10 plus 1 times 8. That gives us now currently a vector because we have this reshape. I can reshape this back to 18 times 18 so we can have a look at it. What public is missing? Yes. So that was the matrix that we've seen yesterday. So it shows interactions of the carbons and the carbons. The hydrogens are down here in darkness. And then there's the carbon-hydrogen and the hydrogen-carbon interaction. Now, what we have to change for our different molecules, our 2,286 molecules, is not the geometry. That's the same. What differs is that thing, more precisely, these 10 numbers. Everything else is exactly the same, but that's, this one here would be the beginning of. So let's have a look at a different molecule. Right, so I did this, I have charges 0. So I can say charges 0, but I have to make this a list, otherwise this doesn't work. So that is for a different molecule. What do you notice? Few things, so the picture now looks different. Before that we had all the diagonals of the same brightness. Why? Anybody know why? Was everything the same brightness before and now it isn't?
Because they're different elements.
Yeah. And the nuclear charges, they are on the diagonal, right? So nuclear charge with itself is on the diagonal, which means the impact of changing the nuclear charges is largest at the diagonal. That's what you see. And you can tell the order, right? Carbon, boron, because lower value, right? So then that is 5 squared, that is 6 squared, and that is 7 squared. So carbon, boron, carbon, carbon, nitrogen, nitrogen. Right? So you can read this off. And let's compare this. Maybe I can show you the sequence. Keep in mind that my charges 0 will differ from your charges 0. So that thing is a carbon, followed by a boron, followed by a carbon, carbon, nitrogen, nitrogen, carbon, nitrogen, boron, boron. Right? So you really see this in the colors, the impact of the different elements, which is exactly how this changes. Now, of course, the all diagonals are also scaled, right? Because they depend on the nuclear charges. But I think it's enough to see for the time being that changing the nuclear charges does change the representation, which is what we want, which is what we need in order to be able to to tell this apart. Make sense so far? Maybe we can also look at this in a different manner if I don't reshape this. This is now plotting the vector. So on the x-axis, you have the components. So that's basically plotting this thing. What you see on the y-axis is the corresponding number value. It's the Coulomb matrix brought down to a single vector. So that's what you have. If we now take the first and the second molecule, then you will see two lines here. So you see they are somewhat similar. There's blue and orange in this plot, right? They're somewhat similar, but the peaks are different and the shape is a little bit different. And that's exactly what machine learning is trying to use. Whether they are similar or whether they are dissimilar, that plot is going to look slightly different. All right? Okay, so now we know how to get our Coulomb matrix. Yeah, I'll leave this here. So now what we're supposed to do is get us 100 of these representations, right? That was the task. 400 data points, let's build some matrices. So we can do representations is a list. So for I in range 100, let's place run this. So that builds us the Coulomb matrix, always for the same geometry, but for the different set of charges for the first 100 entries. So that representation is trying in the plot of what we want to do are these, right? So our 100 vectors. Everybody happy? Okay. Now what we need to do is calculate the Gaussian kernel to build out our kernel matrix. Right? And luckily, didn't copy the function yet, so I have to do it. Luckily, we have solved this problem. Right? So I need to copy the Gaussian kernel, and I need to copy the fit K or R. So now alphas should be fit K or R, where the training XS are now our representation, because they used to be the single scalar values, but now they're vectors. So that would be representations. What are the Ys? What's the property that we want to learn? Energy. So that would be energies, but the first 100 of those, right? Not all of them, but of course the matching 100 ones of the class. Let's see what this works. Look good. What's the size of alphas? Is it a scalar? Is it a vector? Is it a matrix? It's a vector. How many entries does it have? Hopefully. Okay. It contains 100 things because those are the scaling coefficients. Remember this plot from yesterday, this figure? That's the scaling of the kernel function to make it match the true approximation. Everything reasonably clear up until here? Okay, now we have the alphas, which already contain the y's, right? All of this together is alpha. So we can predict. Let's have a look what this works. Huh? So yesterday we also implemented the prediction. So now we can have a look at the prediction of let's test whether the model can predict the training data. Right? It should give perfect prediction for the training data. So let's ask for the first molecule, right? And we need the training XS, that's the representations. This is what we're going to look at. And we need the alphas. Now this is bad. I'm losing some parentheses here. So this gives us now two values. First we call prediction, where we give it all the training data positions, which we need in order to know where the kernel functions are centered. Then we give it the one representation for the first molecule, right? The one that we currently look at. It's part of the training data. And then we give it the alphas that we got from training. And the last thing we get for comparison is the actual energy that we would like to learn. Right? And the answers are identical. Or at least very, very close. Let's see what's the error. 10 to minus 8. That's okay. So this means our model is at least able, let's take the next data point, again 10 to minus 8. Our model is at least able to predict the training data. We can probably agree on the fact that this is the minimum that we can expect from any decent model. So, now the interesting question is what happens if I ask the model something happens? Predict something else. Everything up to 100 is stuff that we know. So let's take the 200. That's a big one, no? We're only off by 398 heart rates. That's a funny problem. Let's look a few numbers further. 201, 2, and so all of them seem to be very big. In fact, let's make a plot of the errors. I think that would be good. Now it needs to do 2,286 predictions. Let's have a look at what's going on. So first you see, our error is nothing. Right? That was the training set, exactly. The training set we have. Yeah. Now, if you have noise-free data, kernel methods must be perfect. Because the alphas are found such that they reproduce the reference data. And after that, we see our error is always pretty high, always around 400. Any idea what's going on?
Is it not possible that you have atoms that are in the training that are not in the test? From charts?
Charges which are in training but not in test. Combinations might happen, yeah. So a particular combination of charges and all that. But generally speaking, it's the same set of carbon, boron, and nitrogen. This is a plot of the energies. So you see that the energies, they contain 1, 2, 3, 4, 5, 6 groups. Anybody studying chemistry or physics here? Can you tell me why I have these groups? What's going on? I mentioned this very briefly in passing yesterday. Maybe the provocative statement, almost everything in chemistry is obvious. It's the fact that you just have the atom, right? So the total energy of a molecule is dominated by the sum formula. That's, and well, how many ways do you have to BN doped naphthalene? I can have no BN pair. I can have 1. I can have 2, 3, 4, 5. Those are my 5 levels of energies that I have here. And this one, the highest one, the single one, there's only one of these. There's no BN pair. By adding BN pairs, I lower my energy. So this is no BN pair. 1, 2, 3, 4, 5. Now, you see that they're slightly different, right? That's the actual difference because of the bonding energy. That's where the chemistry happens. This is just the fact that you have a certain number of elements. Now, let's think a little more. So, are you happy with this? The layers are understood. Okay. Now, the total energy that we have is about almost 400, right? Minus 400, give or take. So the error that we have is also almost 400. It's a funny thing, basically almost always wrong by exactly the total. Let's check what those predictions are there. Let's not look at the errors. Let's look at the number value. So 10 to the minus 299. Fancy way of saying 0. Can you tell me what that means? Basically, almost all predictions that we get are 0. How is this possible? The predictions. Almost all predictions in our model are 0. How is this possible? Every data point is perfect, but every test point, so every training point is perfect, but every test point is totally 0.
distance.
Hmm?
The distance?
What do you mean with the distance? Every point here is perfect, but every other point is 0.
The curve is 9. Zeroing out.
The kernel is too narrow. Kernel function basically looks like this. You have the name that in there. So basically, this means that the representation of the data points are too far away. Right? You have the kernel function which decays very quickly to basically 0 because it's not wide enough. And you can see this. Let's take two representations, any two, right? 0 and 1. What's the distance? 76. That's just the distance between the first two molecules in the Coulomb matrix representation. Remember the Gaussian kernel that we plotted yesterday? We plotted from -5 to 5, right? And that already was basically reaching 0 towards the end. So our kernel is much smaller in scale than our distance between paths. So let's try something dirty, right? Yeah. Let's just divide all our representations by 100. Because that brings us from 17 to 0.7. And our kernel is roughly size of 1. Would be the same if you change gamma in the Gaussian expressions on the web page. It's this gamma that determines the change of distance. So we can just do this in the representation to make our life a little easier. So let's do this. Where's my Coulomb matrix function? I just return 100. So we don't spend too much time on this. Build. Plot the errors, please. And our errors went down quite drastically. We still have errors which are 0 for our training data. That's expected. It will always be basically 0 for our training data. Now our errors went from 400 to about 10. And the reason is because we went in this picture to that. Because now you actually have an interpolation. The Gaussians are wide enough, they can actually get any kind of non-zero prediction a little bit away from the data. Is that intuitive? So now, what would you do if you were to build an actual machine learning model, if you wanted to have a real predictive model? What do you have to do? You have to find that scaling factor, right? So that would be adjusting the width of the kernel, the same way as the day before yesterday, we adjusted the k of the k nearest neighbors to get something which is more reliable. You will do the very same thing here. That's called hyperparameter optimization. So when you build a machine learning model, now you would say, if I have 100 random points, which value of gamma gives me the model of best predictive power? And that's the trial and error. There is one starting point that you can have, because you can say, if my points are this far away, my kernel should roughly live on the same length scale, right? So you at least know the ballpark thing. The kernel function should be able to maybe reach the next point. So the width of the Gaussian is maybe in the ballpark of the same distance between points. That's exactly what I exploited here when I divided by 100 to make this roughly scale. Make sense? Any questions on this? Is there a removal?
But if gamma is too wide, the errors will increase again?
Yes. Let's do it. That's the neat thing of having the code yourself. You can nudge everything. How wide do you want it to be? Wide, huh? So we can see something. Okay. Not wide enough. But what you can already see is something peculiar. Errors went down, yes, but something funny happened. Yeah, for some reason we now get an error in the training data, which means it's starting to become numerically unstable. So usually what you would expect if you optimize this, by and large, what you see, you can adjust gamma, and you can adjust lambda, regularization. With lambda, what you usually see is something like this. So this is the mean absolute error. Usually, on log scale, usually lambda should be very small, like 10 to minus 10, and it should not really matter. Then, as you increase lambda to something big, you start to get strong deviations because lambda at the same time limits your predictive accuracy. If lambda is 1, you will be wrong by on average 1 at least. You can't learn better than lambda. Now, what about gamma? I have to think about it. This looks like high gamma means narrow Gaussian. Yes. So large gamma means narrow Gaussian. So if you have normalize your distance to be roughly 1, right? So we say this is gamma divided by the mean xi minus xj. Then typically around 1, somewhere here is the minimum. And it's usually fairly wide which parameter you take. And then on the y-axis, kind of looks like this. On the one side, it gets worse quite quickly because your Gaussian becomes narrow. You have this nail bed picture that we had in the first place. Or your Gaussian becomes too wide and you start to predict the camera. Does that make sense? Now, I want to emphasize one more thing before we move away from convolutional regression. Remember those 6 layers? Right? You have something that already explains the trend of the data. That's the number of the end path. Which means that you would remove that trend. I can just, in my model, I can add 6 numbers by just taking the average of the energies for each of those levels and subtract them from the y's that I want to learn. So I detrend the data for the impact of the sum formula, which already reduces my error quite a bit. So in practice, what you would do is you would try to normalize your error or your labels that you're learning based on whatever criteria you can come up with in the corresponding trade data. So that would be the formation energy rather than the total energy. But logic is exactly the same. Any questions on convergent regression? The concept of what it does and what the knobs and turns do, is that kind of clear? So you can do the same thing with scikit-learn, but that looks exactly the same as on the first day. So you take the KN regressor, feed in our representation vector here in the method. So I think it's reasonably boring to see. The math is the same, the code is the same, the logic is the same. So with that, I would suggest that we move on to the new topic, unless anybody has any pressing questions. All right, let's do that. All right. Now let's have a look at Alchemy. What is Alchemy? You already have seen this a little bit in the data set, right? So you have the change of nuclear charges in this data set of 50,000 molecules, where the geometry was the same, but the nuclear charge was different. And that's exactly the chemical change in question. So you would have the nuclear charges be different. And the question is, how does the energy change as you change nuclear charges? And that's, quantum chemistry, a well-defined problem. So usually we have the system Hamiltonian. So actually, let me see in show of hands. Who knows what the Hamiltonian is? Okay. So physically speaking, every physical interaction within a system is fully described with the Hamiltonian. That's the core element of quantum mechanics. And it takes the nuclear charges, atom positions, number of electrons, and the net spin of the system. If you have those, that fully describes the properties of any system, provided that the physical effects that you actually plug in the Hamiltonian are accurate for you. But that's not possible. Now, what people used to are changing positions. Right? I have an atom, we look at the Morse potential, that's changing the position. So you have two atoms, they're driving each other, they're bonded, now we can stretch them, we can condense them, and in both cases you pay for that energy. But that's a bonding potential. So the derivative of the energy with respect to position is what? The force. Exactly. The derivative is the negative of the force. But what people usually don't do is take the derivative with respect to nuclear charges. That's perfectly bad. You can do it, and I will show you what you can do with this. So the core idea is, if you have many systems which are similar but only different nuclear charges, just like in our database, then you can do a Taylor expansion. You can say, I take my system, which in this case contains of three things. There can be three atoms, three functional groups, doesn't really matter. Three things, and you take a derivative of how a property changes if you change one thing, or the other thing, or the third thing. Now you can make this a Taylor expansion, where the different modified systems, for example, the first modified system, two have been changed, right? So you take that change plus that change. And since this is a function and derivatives are the same as you go forward and backward, you can also just take the negative of the change and change the first thing in the other direction. So for example, reduce or increase the nuclear charges, and then you have the negative change. Now the beauty of this is you see here in first order approximation, you calculate three derivatives and you predict slightly more different systems. First order usually isn't accurate enough, but it gets the picture across. So if you then say, okay, maybe they interact, right? Maybe I have the change in the first item and the change in the second item, they're maybe not independent, right? Because they're close by, so maybe they interact. there will be a second derivative contribution, because now you change pairs of things. And that's exactly what you do. You build a multi-dimensional Taylor expansion, which is just a very nice polynomial. So the main advantage of quantum alchemy is the fact that those derived systems here I get practically for free. To get the response or to calculate one thing accurately, that's expensive, right? I need to calculate, run a full quantum chemistry calculation, which maybe takes seconds, maybe takes hours, maybe takes days, what you're doing. But once I have the response functions, I can predict something like this in a few nanoseconds. It's just a polynomial. There's another interesting thing which is helpful. Because it's a polynomial, I can look at every term. I can interpret this. I see exactly that changes the property by that amount. I have a direct link between the two. Quantum chemistry, most accurate calculations actually require an iterative approach, so I can only see the summary result, but I can't tell the individual contribution. So we use that to calculate many things at once. So every dot here is a system, a molecule, a material, whatever you want. And the traditional way of calculating something is you pick one, you calculate it, you pick something else, you calculate it, rinse, repeat. But all the calculations are dependent on each other. What we are trying to do with quantum alchemy is to find a way to do one calculation and then predict many things which are similar just from the response functions, just from the derivatives. You can't go arbitrarily far away because there's a Taylor approximation. The Taylor approximation is local, so it has a radius within which it's accurate, but that radius is finite. And oftentimes contains millions of systems. So you can do this for very many different things. You can do this for energies, for densities, for one-dimensional properties. There's a long list of results of properties for which you can calculate this, and we can do this in very many different codes. Today, we will do this in PySCF. Now, probably almost none of you have experience in computational chemistry with PySCF, and that is no problem, because I wrote that code for you, so you can just copy and paste it. But we do the derivatives of that. So you have you will get code how to run a single point calculation for one particular geometry. You will figure out how this changes, how to get the derivative as you move the ends. So technically speaking, how does it work? You take these Hamiltonians. So basically that's the descriptor of the molecule where you come from. Think of machine learning, right? This could also be a descriptor. One point, say this one. There's another point where you want to go to, the target, that one. And now you interpolate linearly between the two. And that interpolation parameter is lambda. Then you can show that you can get the energy of the target by taking the energy of where you come from plus its derivatives. So that's exactly the Taylor expansion. Here's one example how this converges. Let me focus on the left side here. This is actually the change that you will do today from nitrogen dimer N2 to carbon monoxide and the other way around. Why does it work? Well, both have 14 electrons. So I have 7 and 7, and now I can reduce one nuclear charge to carbon, 6, and increase the nuclear charge of the other to 8. And I can start from 6 and 8 and make them both 7. My chemical changes, and do a plot. We will see how the energy changes as you do now. And this you see that with the first few derivatives, this very quickly converges to what people call chemical accuracy. Basically, accurate enough is what we mean. And if you want to continue, you can have more orders, but this is not exactly fun and technically hard. Now, there's a few things that may be a surprise to you, because you can express surprisingly many properties as a derivative of the total energy. So, for example, the force is a derivative with respect to the nuclear position. Right? That's what we just said. It's like, okay, not a surprise. You can say vibrational frequencies you can obtain from the curvature, right? Because that's what gives you the vibration, the minimum one. So that would be the second spatial derivative. But what's maybe not as obvious is that you can differentiate the total energy with respect to external field, and get the dipole moment of the system. You can calculate the dipole moment the traditional way. That would be an integral of the density, the electron density of the system. But formally, it's also a derivative. Same goes for polarizability, for the magnetic moment, coupling constants, IR transitions, circular dichroism properties, NMR shifts. All of that are derivatives of the energy with respect to different things. Which means there is a point in finding a way to get derivative quantities. Now, I'm not saying this is the way how they are calculated, but on a piece of paper, that's the way to get it. So, having the derivatives is a standard problem in quantum chemistry, and B has its use cases both for quantum alchemy as well as for getting those properties that you can observe experimentally. So you know the forces. It's a practical thing to do. You know the Hessians. That would be the second order derivatives, which you use for the corresponding vibrational spectrum. But what do you do if there isn't some grad student 10 years ago that has implemented the derivative you care about on chemistry for life? What do you do if you have no derivatives, no analytical derivatives? Yes, there is a hammer for that problem that almost always works, but as it works. And we will use that hammer today. It will remind you of high school math. So it's called finite differences. And the idea is you do exactly what you know is the definition of the derivative, right? So the definition of the derivative is you take a function value at one point, slightly close to that, you take the difference on the y value, divide this by the difference on the x value, and you take the limit expression as these points approach zero distance. Now, you can do this numerically. And it's called finite differences because the distance here between the 2 points that you evaluate is non-zero. It has a finite but small value. The good news of this, no matter the function, this always works. The bad news, it's noisy. Why? If you make this distance very big, you're wrong because you're not actually taking the limit towards small displacements, right? You're just evaluating the volume. If you make this displacement tiny, then you run into the problem that your computer is not doing actual math. It's doing a finite precision math. You only have something like ballpark 15 significant digits in the floating point numbers that you use. Which means that once your energy difference becomes very, very small, or the function difference becomes very small, or that displacement becomes very small, then 15 significant digits are not enough to be accurate. So for very small displacements, you're wrong because of numerical precision. For very large displacements, you're wrong because you're not actually taking the derivative. Make sense? This is what this would look like for quantum chemistry problem. Delta is the displacement. So the distance between the 2 points at which you evaluate that, this is the absolute error of your derivative. You will produce this quantity. What you see is that if you make the displacement very small, then the error is large. And if your displacement is large, your error increases again. And this is actually the superposition of two sources of error. You have this line, right? For very small displacements, delta, and this is the next error. In the limit of very small displacements, run to the problem of finite precision. The floating point numbers of the computer are not sufficient to resolve the energy difference anymore. So, well, that of course goes away as you make displacement larger. Right? That's why that effect always looks like this. But remember, if you make a displacement very big, you're not actually taking the limit of small displacements. It means you have that error contribution, which vanishes for tiny displacements. For tiny displacements, you're taking actually the limit of delta towards zero. Large displacements, you're not. Since you can't isolate either of the two errors, you get the sum of them. Which is exactly the V shape that you see here. Where that minimum is located depends on your property and implementation, and yada yada, right? Direction of the wind. So there's very many reasons that influence this. The overall shape is almost the same. Exactly because you have these two effects that always interact with each other. Is that possible? Which also means that in finite differences, you can't just always say, oh, I take delta to be 10 to minus 6 because it works in this case. It's brilliant, maybe it doesn't work for the next one. Since only a few of you said they know what a Hamiltonian is, that slide is probably too much. So let's skip the Hamiltonian forces and let's look at the tasks. So maybe it's important to mention that in quantum chemistry, those derivatives are not calculated, typically not calculated by finite differences. And the reason for that is that the approximations that you make to have an efficient, numerically efficient quantum chemistry calculation are not very well compatible with the derivatives. So the approximations are designed such that the total energy of the system is correct, but not that the derivative of this energy is correct. Which means you have to calculate the derivative explicitly. That's not Right, do you have any questions on the slides? All right, let's try the first task, and then after the first task, let's take a break. So now, if you go back to the course page, there's quantum alchemy again with the slides and with the tasks. So Google Colab does not have PySCF, but if you just enter this here, don't forget the exclamation mark at the beginning. If you just enter this, then you install PySCF on Google Colab. Don't forget it. So let me quickly walk you through the idea of the first task. You remember the first day where we did work with the force protection, right? There was a 1D function that showed the bonding potential. Moore's potential was this, right? Now, that was an analytical expression. We set all the parameters to 1, right? And then we got this curve. What we're going to do is we're going to calculate the real deal. This Moore's potential is a classical approximation. There's no quantum mechanics involved. So now we're going to do this properly. And that means that we simulate, in this case with Parte Falk, we simulate what the answer would be according to quantum mechanics. So taking electronic effects into account. Good news is we only do this for dimers. Today you will only run calculations on dimers. This has a nice advantage of being fast. Those calculations typically scale with cubically with the system size. If you want to run caffeine, be my guest, just bring some time. Let me quickly explain what the ingredients are. This is not a course on quantum chemistry because you didn't do a theory on quantum chemistry. I at least want to motivate what the individual ingredients do so you have a rough understanding of what the code that I give you does. So PySCF is a Python package that can calculate or simulate quantum chemistry calculation. And it's a competitive research level code. It's what we use in our research groups. And we load 2 of those components. So first we build a molecule. This Morph thing is a class, an object in Python that represents a molecule. And what do I need for a molecule? The atoms, right? What element they are, and where they are located. Right? Nuclear charges and positions. That's the first thing that enters here. The one element, and then X, Y, Z. Second element, X, Y, Z. Now, if you run a quantum chemistry calculation, there's also the quality setting. I will not go terribly much into detail what it is, but it's called the basis set, and it's a measure of quality. There is bad basis sets, which are cheap. That's what you're going to do. And there are good basis sets, which are terribly expensive, which is what you're going to do once. And first, we define a molecule, and then we run the calculation. Because on the same molecular structure, you might want to run different calculations. That's why it's separate. And this kernel here has nothing to do with the kernel function. Right? Don't be confused. This has a long-standing reason. This calculates the images. So this is probably the minimal way to run a quantum chemistry calculation in PySCF. So you create a molecule where you run a certain level of theory, a certain calculation, and then you return the energy, which gives you 1 point. Because the function takes this argument, distance, that specifies how far away those 2 atoms are going to be. That's why you get this curve. For different distances, you can run the calculation. And that's exactly the first task. So produce that curve for, say, N2 for CO. Any questions? All right, let's take about 5 to 10 minutes. I should be reasonably fast.
I have some strangers. Doesn't much. You have like oh yeah. The other, but here the problem is setting too old. Is it correct? It's because of the scale I said. It's not good to see. This one is true, this one is this other one is not. Hopefully it doesn't die. But for one of them, this one is CO. Maybe I should find the range. Doesn't have words.
All right, let's do this together. Come on. Let's do this together once more, and then we take a break. All right. So I just copied code, and we test whether it works. So dimer energy, where the one element is a nitrogen and the other element is nitrogen, and let's say they're one angstrom apart. And you were supposed to take the install myself. So that gives me one energy, and now I can do something like access to be from 0.8 to 2, let's say 10 things would be dimer energy, all of that for different values, and then I can see what this, while this is running, I can explain what the code is doing. So first, we use a number in space to get equidistant points with some range from 0.8 and to 2. And we take 10 of those, so we don't have to wait so long, because the standard is 15. And then we calculate the dimer energy for Nn for a given distance using that quality setting. We plot it, then we get a beautiful curve. Of course, it's so discrete down here because the number of points I can check. And now I can change this to say CO, and let's take a few more points. Run it again. And this is the bonding potential for CO, which looks slightly different. Now we can plot both of them on top of each other. And just for illustration purposes, let's take 5. So which one of the two is higher in energy? CO or N2? Even if you know nothing about chemistry, you now know this. Remember when we looked at the BN doped naphthalene, there were 6 levels. What was on top? All carbons. But polarizing the charge from carbon to boron nitrogen, so piling up electrons around one nucleus, that was lower energy. Which means that this is nitrogen, and going to carbon monoxide, polarizing a nuclear charge, gets us lower energy. So that's N2, that's C. Now some of you maybe got some wiggles. Right? If you go to very far distances down here, then maybe you got something like this. Huh? The reason for that is that the quantum chemistry method of Falk is only able to describe the region around the minimum. It's neglecting effects which play a role for our association. Does everybody have roughly this or something like it? Because you will need YCF for the rest of them. The main reason of this first task is to make sure YCF works for you. If not, let me know, and then let's take a break. Implies having a delta which is non-zero or small. So now you have a function to evaluate the diamond energy. That's basically what F is here, right? Now you can calculate the gradient, so the force acting, negative of the force acting on the system, by calculating the energy once at a given position and once a little bit to the side, and applying the equation. So you evaluate the diamond energy, let's say at 1.1 and at 1, and you divide the difference by 0.1, because it's the difference. Make sense? All right, now you can do that for different displacements, so different deltas. And then what you're going to see is the effect of that plot, right? The V plot. Because if delta is too small, you get a big error because the derivative is wrong. If there's a precision that is lost, and if delta is too big, you lose because you're not actually taking the limit. So then that limit is not taken. So now the task is try out with different deltas, calculate the gradient, and plot it. For comparison, I gave you the exact value. Right? So that's why if you do this for n2, for x0 is 1, and you leave the settings as is, then that is the correct value. So you know at least which of the many numbers that you get is correct. So try to do this plot that you see on the top right, based on different displacements. Any questions? All right, let's try it.
So I need to calculate that energy once, and the incremental distance will be calculated again. But I need to do it for all the points. It's equal to so you just need to put this down. Don't use that. If you don't have a function, don't have any arguments, just no.
Change this, for
also mix of other words, but I could plot this. It's a bit stupid. I was able to both of those as well. So what I was very detailed. And then I have this prediction of the delivery. So I should just plot the prediction of the types. I didn't show. Tem que fazer o derivado. E no X o seu código da nossa assinatura de acho. Depois eu tenho 10 colheres. Depois eu fiz já com o lado. Eu vou aqui em vez de fazer. Se você vai fazer isso aqui, você vai fazer esse cálculo aqui. Então, cálculo de x igual a esse valor aqui, de x mais o mortal, que você aplica essa fórmula no derivado. Fiz uma cara aí. Então, isso tem que variar assim. Você diz a curva. Então, você vai colocar a diferença finita. F de x mais h, f de x sobre h, delta é h, que eu aplico do cálculo. São h, mas é a mesma coisa. Só uma coisa vai e aí você faz tudo para dar as contas de deltas. Dá para fazer tudo isso com isso. Dessa vez, essencialmente, tem algo de derivada mais específico. Mas ok, não. So as the delta increases, here it is very close to the red, and then as it gets higher, the absolute error would be Having growth testing. I try to make a priority. I try to open that. Why? I was doing like this, then everything was because of the fire. I was able to want. So this is the first class. But then the second one, I don't understand how is it can be deep and then go down. Yeah. It is really the difference. Just not the best. The size of this. Sorry. That's it.
What is the
ponto 2 é x mais h e o outro é x. E o x é negativo. X igual. E quando você for usar para ver aqui, ele vai dar uma próxima. Oficialmente, ele sair depois que você botar o erro. Foi todo o processo.
Ah, ok.
Não, nesse caso, só faz f de x mais delta x. Sem falar.
Once the real
Ah, tá. Não sei. Essa escala, tá? Veja bem, o delta, ele está o delta, você está em uma escala que está mudando 100 vezes. E o seu eixo não, você tem que fazer se você colocar a venda certa, deve ter semi-log x ao invés de log.
So that's what this is. There's a list of things that we can do. There's no point in so you choose what this is. And this is all
I thought it was just a fix
Vai ser só
or pre-computed with the linear position.
no. That's why it's set the position.
também próximo do valor.
I thought it was really
Você deve nos quatro, vai
So that's why you can choose the position.
okay, so you really
But you can do this, right?
Yeah.
So that's exactly the difference. If you think that reference was target. So the reference would be just some solvent. The target is solvent plus some set of point charges. And the difference which you would choose is these terms times whatever charges.
Yes.
That's why you can
So that's the derivative of this.
You can do the trick with the energy density. Take any observable. Because if I
né? Daí tá um lado em cima do outro. Daí dá pra fazer certo explodir. Uma estação atômica.
The same concept, 18 approach but it doesn't work, for example, over the state or portrait. Everything which is a unique definition, it is volume. And the platform.
E agora tá tem uma missão de vocês, você pode conseguir.
If I can do that, I probably would say that. This is the worst problem. Problem is something like this, we change something potential. The basis vector is this should be much more clear. So that will be maybe also some other applications. Maybe there's also other applications. Yeah. Whatever you change.
It's a very quick way to do
So the second one, is if you do this, it's maybe 40% silver, same point price. Then the gradient, it represents cost is probably 71, maybe twice. Unless you go crazy, right? The cost of the skates with memory, especially the memory. Because you have to keep the track of other whole trees. If you do further derivatives, you differentiation by minus basically differentiate the code because you just differentiate which goes on the whole trees. The other thing is you can memory to put numbers. So if you have 1,000 numbers because you want to do this for agriculture, then you're going to pay 1,000 for gradient, million for.
There will be distribution.
Yeah, but you have to put them somewhere.
Yeah, but if we go with what one that just said,
This would be very steep.
yeah, I know, but
Yeah, if you put it somewhere. So then the derivative becomes expensive. So if you have so many things that would make more sense, you take the derivative with the integral differential. So with this eigendeposition as well, then I would probably take differentiate with respect to the full change. So it would be, if you take all partial derivatives, you put the prefactors that would go here, already when you differentiate this one direction.
Yeah.
First or second. So then it becomes cheaper. That would be this Jacobian vector. Then it depends, right? If you can do the projections, many points to predict, you can't do it. But you can take the full Jacobian vector. Then every projection is able to actually have to trace the call graph once.
Acho que você deve estar negativo.
So basically, depending on how many variables there are, different strategies can be cheaper.
ask you what this is an alchemical change, right? Like, how can I say that just some information regarding it? Or it's like, I don't know. So the opposite is 300. So I will put something here, and then it will increase the charge and increase the other one. So from this one, I need to one and one is one.
Right, let's do number two together. All right, so the task was to get the finite differences using our dimer energy plot. So we can first try one displacement. So get derivative where I say this is delta, and I say so supposed to do this at a certain location. So we can say A is 1 plus delta, and B is that 1. Return A minus B divided by delta. So get derivative of 0.01, just have something small, is minus 1.32, that's roughly the correct value. All right, so now we have something where we can put different values of displacements, and we get slightly different derivatives. Now, one thing that is worth noting, that is always the same. What is this doing? Okay, so let's call this center. Let's call this center, and then we can actually move it out. Makes our calculations faster. So we can say, let's do different displacements, deltas, going from minus 10 minus 10 to 0, minus 20. And derivatives would get the derivative for delta in deltas. Now, we know the reference value because I calculated the correct value before. So this is now the average error. Let's go through step by step what's going on. So first we have a function which calculates a derivative if we know the answer of the evaluate center, so where we would like to evaluate our derivative for a given displacement delta. So we do this once, the actual calculation of the displaced position. Now we return the first order derivative by taking this. So we calculate the center once, we calculate choose different displacements, and now we calculate the corresponding derivative for each of those entries for different displacements. And when we do that, we can make this log plot where on the x-axis you have the displacement, and on the y-axis you have the absolute error to the true one. And we see exactly the same V-shape as on the slides for exactly the same reasons. If you go to left and right and unstable, that's why you see the oscillations. That's the consequence of numerical instability. And on the right hand side, you see the error increases. Just because you don't actually take the derivative. Any questions on this here? Okay. So far, there was a preparation on how to do numerical derivatives in quantum chemistry applications. Now, if you copy the new code here, you can do a chemical changes. Now you're going to do quantum alchemy. And the code does the very same thing. It's just lengthy because it's a little bit harder to convince myself to do a chemical changes. The core idea is, again, you build a molecule, you do a calculation, and then you change the internals to actually represent a chemical change, where you now can do fractional elements, something which is halfway between nitrogen and oxygen. So that's how you do atoms with a nuclear charge of 7.5. Okay, so there's one additional parameter. So the distance is the same, so the element is the same, distance is the same, base is the same as before. There's one more parameter, which is the chemical change. And what it does is what you see here. It increases the first element's nuclear charge, and it decreases the second atom's nuclear charge by an amount that you specify, so a chemical change. Means if you have N and your chemical change is 1, then what you get is OC. Because you increase the first nuclear charge, you decrease the second. If you have N, and the chemical change is -1, you get what? CO. Because now it's always a multiplied. If you have CO, the chemical change 1, you get what? Increase the first, decrease the second. CO and -1. It's not much. Now decrease the first, increase the second. Who knows the periodic table? BA. Does that make sense? All right. Now, good news, or the good task is now to actually plug this. You can just copy the code. And what we would like to do is we would like to see how this how the energy changes. So what you do is you can plot the change going from CO to N2 in steps, so you show the energy as it changes, going from CO to N2, and the other way around, going from